6.2 Volume by Revolution Washers. The look of the little piece of volume is going to have a different look. It's going to have a hole inside of it, so we can't call it a disc, we call it a washer. And here's the theory. What we're going to do is we're going to find the area between two curves. We are going to take a representative rectangle and we're going to revolve it, in this case around the x-axis, and it's going to create a washer. This is the area of the base. And this area of the base is really the big circle minus the little circle. So this is pi big R squared minus pi little r squared. And that creates the area of the base. When we multiply it to the height, we create the washer. So delta V is equal to the area of the base times the height. And so this will be pi big R squared minus pi little r squared, which creates the area of the base, and then times the height, delta x. You can factor out the pi and have this, and then you write the large radius in terms of y, and so that'll be the y of the upper, and then the little radius right here will be the y of the lower, and if you replace that and set it up in an integral, that's what you get. Let's go ahead and start from scratch on a problem. We're revolving around the x-axis. I'll go ahead and draw my reflection here. So you kind of get the feel. I am going to draw my rectangle, and that's going to look like this. It's going to create this washer. And this will be big R, and this will be little r. So delta V is going to be the area of the base times the height. The base will be pi big R squared minus pi little r squared times delta x. That's going to be the height of the little washer. So you can factor out the pi, and the big radius is always the same across here. It's going to be 2 squared. And the little radius right here is actually the y of the curve, quantity squared delta x. We need to replace that y of the curve, and the y of the curve can be replaced with root x, quantity squared delta x. Now the washers are going to be stacked from 0 to 4. And the reason I can do that is because I'm setting y equal to root x and 2. I'm trying to find the point of intersection, so root x is equal to 2, therefore x is equal to 4. So the volume will be from 0 to 4. If you want to take the pi, put it outside the integral, and then that'll be 4 minus x dx. And here's my solution again. Okay, let's go ahead and get started. This time we're going to revolve around x equal to 4, and x equal to 4 looks like this. I'm going to go ahead and draw my reflections. So I go out to 8, and I kind of get a good look at what's going on here. I am now going to draw my rectangle, which is always perpendicular to the axis of revolution, and it creates this washer. And the little radius will be right here, and the large radius will be right here. So a little delta V will be equal to the area of the base times the height. In this case, it's this ring here, which is pi big R squared minus pi little r squared, and our width now is delta y instead. I'm going to pull out the pi, and then I have to figure out how to write the big radius, and the big radius is always the same, it's 4. And the little radius right here is going to be this distance right here, and so the whole distance is 4, and then I have to take away this distance, which is the x of the curve. Quantity squared delta y. I can make this 16 minus 4, and now I want to replace x of the curve. So I'm going to solve for x. X is equal to y squared. So this will be minus, and I'm going to substitute x of the curve to be y squared, quantity squared, delta y. I'm going to go on to the next screen so you can see the rest of the solution. And it's going to, the stacks of washers are going to go from 0 to 2, so I go from 0 to 2, and I write out the integrand. On this next problem, I want to revolve around y equal to 2. Let's go ahead and draw the reflection. Just so that you can get the feel here, I am going to draw the rectangle, and it's going to create a washer that looks something like this. This will be my little radius, and this will be my large radius. So delta V will be equal to area of the base times the height, which is going to be pi big R squared minus pi little r squared, and in this case the little heights are delta x's. Factor out the pi, and my large radius right here is 2 take away, and then I have to go down here to y of the lower. So I want this y right here, quantity squared, minus, and this radius will be 2 take away, and this time I want to take away the upper y, so y of the upper, quantity squared, delta x. Now the y of the lower is right here, so I'm going to replace this x squared, squared, and then y of the upper is right here at y equal to 1, so it's going to be minus 1, quantity squared, delta x. Okay, I'm going to finish it on the next slide, and you can see I have the same thing, and I'm going from -1 to 1, but to make my integration easier, I'm just going to go from 0 to 1 and double so I can get twice as much volume, and do a little simplifying on my integrand. Okay, and now we're going to revolve around y equal to -1. Let's go ahead and draw that. And I'm going to copy my reflection here. And I'm going to draw my rectangle. And then draw a representative piece of that washer. And this will be my little r, and this will be my big R. So stop the screencast and see if you can go ahead and finish, and the solution is on the next slide. And here's the answer. I take the y of the upper minus, so when I'm trying to find this large radius, it's the y of the upper minus this, which is -1. And then when I want to find the little radius, it'll be the y of the lower, which is the parabola, minus -1 quantity squared. I go ahead and put all those in, do some simplifying, and then I can get my integrand. And there are two ways to get it. Okay, last one. Go ahead and start from scratch and see what you can do. And here's a solution.